Hey everyone, in this video I'm going to go through how to set up an AM transmitter in GNU Radio, and I'll touch on a bit of theory as well, but I'll try and keep the maths to a minimum, although there will be a bit of addition and subtraction and a touch of division, but you should be right. So anyway, just rip straight into it. Okay, so I'll just do something simple. I'll put a couple of signal sources in here. So you can just do Control F, start typing it. So signal source over here for the block, one there and another one. Okay, and these blue things means it's a complex number output, and you can just use up or down to get it to the orange one, which is for floating point. We'll get to complex later, but for now just have a simple floating point numerical output. The other one we'll have is a time sync. So that's basically an oscilloscope, and again make it floating. And on that I want it to have two inputs, so just go to the settings of it, go down to the inputs and click 2. And you'll see that there's 2 there now. So I want to put them in there, but because there's no hardware anything, it's all software, it'll just run as fast as a computer can. So I've got to put a throttle in there. And again, make it float just anywhere along the chain, just to provide some sort of real world timing. So put that in input 1 and that in input 2. Now the frequency for these, I'll make the first one really low to make it really evident that it's different. I'll make that 20 Hertz and I'll just leave the other one as 1 kilohertz. So they're both going in there. Okay, I've just saved that file. So when I run that, you see the two waveforms here. One's the low frequency one and one's the high frequency. I'll just middle click this, bring the control panel up and stop it so you can see. It's nothing that exciting at the moment really. It's just two waves both coming into the scope here so you can see them. What I'll do is I'll go into the config of the scope here and make the line width 3 just to make it a little bit easier for you to see. Okay, so there it is. Two waves, very simple. Okay, now what I'll do is I'll mix these two together. So still need the throttle, but I'll take that one out of the scope and put this back to one input. Number of inputs 1. And from here I'm just going to put a multiply. So there's multiply, just make that a floating block. And here I'm just going to feed the two signals into this so they multiply each other, and then just go through that throttle on the way out. Okay, so if I run that, I'll have a look what goes on. You can see this sort of different thing here. And I'll just pause that and we'll have a look. So just press stop on here. I'll stop somewhere better. Okay, so what can you see? Now first of all, this is the time domain that we're looking at here. When I put that block in, it was a time sync. So this measures the time period between certain points on the display. And if I come back and have a look at the frequency that I set for that higher frequency one, it was 1 kilohertz. So the time it takes for one full cycle to happen of 1 kilohertz is 1 divided by 1 kilohertz. So 1 divided by 1000 is 1 milli. So if you look at one of the peaks up here and you see the time, it's just about 4 milliseconds there. So it'll be 5 milliseconds at the next one, then 6 milliseconds and 7. So that's how we can tell the frequency and the time. They're related, of course. So that's what happened when I multiplied. Now I'll make that a little bit clearer. So where I've got these as a mixed output, what I'll do is on my time sync, I'll put 3 inputs on it. 3 inputs. And for the config, I'll make them all 3 wide. Okay, but this time I'll put the mixed output on the third one there. I'll put the original, what should I do? I'll put the high frequency one in the first input, so it's us about here now. The low frequency one on the second input. So what I'll do is I'll label those inputs in the config for the first one. I'll call that the it's the high frequency, which we'll call the carrier, because that's what it is. We'll get to that. The second one is the low frequency. We'll call that baseband. And the third one is the mixed one, the one that's been multiplied. So I'll call that modulated. That'll do. Okay, if I run that now, there we can see the 3 waves. And what I'll do is I'll just put my control panel on again and zoom it out a little bit so you can see a bit more. Actually, I'll zoom in and I'll stop it at a good point, hopefully. Okay, there's a good one. So now let's have a look at what we got. Okay, so the original signal, that carrier, is a 1 kilohertz signal. So there it is. And it toggles between 1 and -1. So it's centered around the 0 point, and it just does that thing, right? The next one I had, piss that off, was the low frequency one. And it too bounces between 1 and -1, just a lot slower. As you can see, it takes more time, and if I zoom that right out, you'd see the whole cycle. But it's still in positive numbers here, and then it swings down to negative here. So that's those two original signals. Now if I show the result of the multiplication, you see this. Now it's simple multiplication. So if you look at the original blue one here, and we multiply that by the red one, we get the green one. So the blue one here, this value where it's nice and easy, is 1. When it's up the top, its value is 1. So 1 times whatever the red one is here, which is about 0.5, 0.6, 0.6 and a bit, 0.7, you can see that the green one is also that point. And same for all the others really. So when that's 1 times whatever the red is equals the green. 1 times whatever the red is equals the green. And on the negative part, we've got -1. So -1 times the red, which is about 0.5 up here, means it's going to be -5. So it's just simple multiplication of the two waves as far as their values go. And you get this sort of pattern here. Now remember a second ago that the spacing between these was about exactly a millisecond. So if I look up here, it's about 3.7 milliseconds at that peak, which means the next one will be 4.7 and then 5.7. That seems to be what it lined up as. If I go here where it crosses over, have a look at the green resultant wave. So its peak there is at 2.7, 3.7, 4.7, 5.7. Now if I go to 6.7, which is here, it's not a positive peak anymore. It's now a -1. And if I go to 7.7, so every millisecond on now, it's in the negative side of things. And that, of course, is because the red became negative, so it's a negative number multiplied by the first one. So what's happened here is that that phase has that wave has flipped over and the phase has changed. So if I just let that run and zoom out a bit so you can see the whole thing, a lot of books sort of show you, I'll get rid of the carrier and the baseband, just show you the resultant wave. You see that sort of thing there, and that's AM, true, that's amplitude modulation, because we're changing the amplitude by mixing the thing. The problem is, every time it passes 0, its phase changes. So it does that, phase change, phase change, phase change. And we don't actually want that for a transmitter. So we have to do something about that. Okay, so just neaten this up a little bit here. There's our baseband here. And when I say baseband, that's the low frequency information that we're trying to transmit. Okay, so just neaten that up, try and make it clear here. So the low frequency one is this one here that I've currently got at 20 Hertz. So what I want to do is raise that up a bit so it never causes it to go into negative numbers. And the easiest way to do that is add 1 to it. So just add constant. Okay, flip that to float. And I want to put that after here, which means these need a bit of rearranging. So they have to come from the output of that now. Okay, so I've just added 1 to it. If I run that now, let me dodge your control panel on. By the way, hang on, before we go any further, on this scope, you can set it to have the control panel. You can set it to have the control panel, which I'll just say yes because I'm going to be using that all the time. So at the moment I've still got what we had before. You can see everything's there falling between 0 and 1 and -1. But if I, in that constant, add a constant 1 to the baseband here and run that now, I'll just auto scale it and pause it there. What you can see is the original carrier, which is blue, is still the same between -1 and 1. But my baseband now has been moved up, so it swings between 2 and 0 rather than -1 and 1. So when you mix them together, you get this this signal here. Now, if I just let that run a bit, and zoom out. Oh, wrong one. Zoom out a bit and do that. Might even go a bit further. Have to auto scale every time. That'll do. What you can see is now the modulated wave, that green one, it still toggles up and down according to the baseband, the red one, but it doesn't actually flip over anymore. Its minimum there is right on the mark. So it toggles between 2 and 0. That's good. That's the wave shape we want. Like if we just look at that wave itself, that's what we want. I'll zoom that right out, auto scale, bang. That's beautiful. So now it stays in phase. I'll stop that so we don't have a fit. That stays in phase, so that's good. Only problem is it swings between 0 and -2 and 2. And I only really want it to be between -1 and 1. So still got a bit of work to do. What I essentially want to do is just, now that I've moved it up 1, I just want to divide that by 2. So in here, I'll go for divide. Okay, piss them off again. So the output of that, the output of the existing one that we just had, I'm going to divide that by 2. So I need a constant source. So constant source, type float, and the value is 2. And put it into there. So that will divide that by 2. Now get that output and put it in there and see what happens. Okay, zoom out a little bit here. Auto scale, pause it. That's looking better. So now I've got the modulated output, the green one, and it's modulating nicely according to the baseband wave here, and it goes just between 1 and -1, which is what I want. So I'll take the carrier and the baseband out of this. You can see that that's the AM signal that's looking good. So it looks like the one I did a few minutes ago, except the phase doesn't invert. So it goes between its maximum and its minimum without inverting. If it did invert, by the way, that would be overmodulation. We don't want that. So this is exactly 100% modulated here between maximum and minimum. Okay, now what I'm going to do, instead of having that signal source here, just that wave, I'm going to get rid of that, and I'm going to put in an audio source, which is the sound card, which is this microphone. So if I go there, I have to pick the sample rate, and the sound card rate 48K, which, as I said, is why they made the project 48K in the first place, and just feed that in. Now if I run that, what you'll see, let me get rid of the carrier, because it's, the carrier, it's just a standard thing that stays the same. What you can see here, actually, okay, one more thing I'll do is on the scope here, the update period, I'll just make that a lot less, so it updates faster, it'll be closer to real time. So now, you can see where we're going with this. The carrier wave, the blue one, I'll just get rid of that, because you know what that looks like, it doesn't really change. And this should be a lot clearer as to what's going on if I find a nice spot here. Now that'll have to do ya. Now what you can see is when I don't talk, the modulated output, the green one here, just looks like the carrier. So I've just paused it. That's my voice here, the red one, and when I'm not speaking, it's not modulating the carrier at all. So it's just a solid, standard frequency. Beautiful. But when I start talking, if I pause that, that's probably a bit rough. If I pause it at a better spot, okay, that'll do. What you can see now is my voice here, the red one, is modulating the carrier to produce this green one here, where of course the frequency is still the same. It's still, 1 millisecond between each cycle, because it's still 1 kilohertz in this example, but the amplitude is totally dependent on my voice. So if I put the baseband back on, the carrier back on, it's still a multiplication. So the red times this blue equals the green at any point along there. So if I take the baseband off that and just run it, that's what you end up with. So the amplitude of that frequency changes with my voice, and it never flips phase. So that's about that. One thing, if I just go to the modulated, just my voice there, ideally that would go between 0 and 1, but it's a bit low there. So I can put some gain in, or I could just shout into the microphone. But for this exercise, that'll do fine. And yeah, that's how it works. Now if I just go back to where I had just the two simple frequencies mixing directly, okay, so I had that, as one multiplied by the other. As I said, we're looking at this in the time domain, but what I'll do is I'll chuck a frequency sync on here. So in the instrumentation, we've got a frequency sync, and again I'll just make that floating point and give that some input as well. Now the other thing I'll do, like I did before, is I'll change the update period to be nice and quick. Now if I run that, you see we've got a whole bunch of frequencies here, and I'll just zoom in down on the bottom here. What you'll see from 0 on the right here is you'll see the first frequency plus the second one. So the original was 1 kilohertz and 500 hertz. So you see a 1.5 kilohertz here, so that's 1000 plus 500, and then you got the 500 hertz here, which is 1000 minus 500. Now you also have the negative sides, which I'm not going to dwell into just yet. We'll wait till we get to complex numbers and convolution and all that sort of stuff. But I just wanted to show you that there's more than one frequency now coming available. And if you remember, actually I can make that simple for you. What I'll do is just go to the frequency sync and put it as a half spectrum. So do that again, you'll only see the positive, just to keep it sort of simple for now. So looking from 0, you can see that 1 kilohertz is there, but there's no signal there. Instead, it's got a signal 500 above it and 500 below it. Okay, so if I made that baseband signal 400 instead, and did the same thing, okay, have a closer look at that, you'll see that that's now 1400 and 600, because that's 400 off 1000. So you can see what's happening here. The frequency of the baseband that we're mixing with the carrier will determine essentially the bandwidth of this thing, because the higher the frequency, the more it spreads out from the center. Okay, so just keep that in mind. Okay, so going back to the other one, if I've got my voice modulating between 0 and 1 here, let's have a look at that on the spectrum. So just put frequency sync on, and make it a float, put it out from there, bang, 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 update the time there, run that. Okay, well you can see, there's our frequency. Again, I've still got the negative one on there, but actually again, I'll get rid of that to make it simple. Make it a half one, blah, blah, blah. Put that there, run that, zoom in a little bit. So you can see the carrier frequency at 1 kilohertz. And there's extra energy here when I speak, so you can see that there's some energy on this side of it and this side, and it'll be the same, just inverted. If I try and speak really loud, I'll never match what that carrier is doing with such a high duty cycle, so I'll never get up to that. But what you can see is we have these sidebands, and it's due to the mixing, pure and simple, like I just showed. Okay, forget about all this stuff up here. Yeah, so that's basically AM, and there's its carrier with a couple of sidebands. Okay, so that's that. What I'll look at now is transmitting something. So for that, I'll use the old Osmocom sync. For the Osmocom thing here, that's going to be my hack RF, by the way, which is capable of transmitting. Now that has a complex input here, so I need to convert these floating values into complex ones, but that's pretty easy to do. So what I want is a type converter from float to complex. Okay, now from the output of that last one, just bring that into the input of the float one, and for the other, I need something here, because this is real and imaginary. Okay, that's the complex numbers, so this is, and then it just spits it out as a complex output. But we don't have anything for the other ones, so I'm just going to use a constant source of 0 for the other side. Okay, so that'll do. And if you remember, that was my modulated voice between 0 and 1. So that can go into the hack RF. Now I've got some things on here. We've got some stuff we can set. Now I'm just going to use an allowed frequency, like 930 meg. So that's the frequency I'm going to transmit at. And the gains, well, the gains are all over the place. So what I'm going to do is set some variables, because I might want to play with those gains. Okay, so what I'll do, similar to what I did, I haven't done it yet. Okay, so what I'll do is over here, I'll put a range little thing in here. That's just a GUI tool here, and I'll call it the first one, RF gain. And the default value I'll make, I don't know, 10, whatever. Starts at 0, stops at 30, with each step worth 1. Okay, this will make sense in a second. And I'll copy and paste that again, and paste another one. And what I'll do is I'll call these, that one I'll call that IF gain, and this one I'll call broadband gain. So there's 3 different gain values here from a GUI. So in the actual Osmocom thing, instead of giving them distinct values, I can call it RF gain, IF gain, BB gain. So now, if I press the button, I've still got all the stuff we had before, but now I've got some gain values here. Okay, so that's that. Now theoretically I was just transmitting at 930 meg, but see all this underrun here? That's because the rate of this whole thing so far is 48 kilohertz, but I can't use that as a rate on the transmitter, so I have to boost this rate up a bit, quite a bit. So what I'm going to do is make this sample rate, instead of being 48k, I'm going to make it 1.92 meg. Okay, and that is 40 times the rate of 48k. So what I'm going to do is resample this, and I'm going to use a rational resampler. And the word rational, by the way, in this sense means like a ratio. It took me a while to figure out what they mean by rational. It's the ratio. So where it's got interpolation and decimation, that basically means multiply and divide. They're just like making it a pain for you. So what I'm really doing is I'm interpolating or multiplying by 40 times, and that's it. So what comes in as 48k will come out as 1.92 meg. So if I run that now, nothing fucking works. Don't lie to me. Alright, now it works. Gets a bit scared. So now I've got these that I can do, but that's not going to change anything on this display because this is the display before it got to that. Okay. Now for the display on this, I'm going to use a real display. So what I've got here is another SDR receiver, just one from a Raspberry Pi, just centered on 930 meg, which is what I'm going to be transmitting on. So if I'll just run this again and try and show both at once here, which I'm going to struggle with. Okay, I should be able to tweak around a bit here and get some sort of signal. There you can see it just coming up there. Bit of a mess actually. Okay, now theoretically, if I zoom in on that, there's a carrier, a couple of sidebands. Now if I speak, there's a bit of a delay because it's coming from the TCP server, but if I listen to this, I get a hell of a beep. Oh, that's not right. Oh, you can probably hear. Turn this crap down. I'm an idiot. I've missed a whole bunch of things. What you heard was the 1 kilohertz tone as well. Because before, I was just showing this on a spectrum analyzer locally. Okay, so I had to mix my baseband, my voice, with some sort of high frequency oscillator to show it. But in the real world, this is the oscillator, the transmitter. So I've got to modify this a bit. I don't need that high frequency, well, what was a high frequency source, because that's going to be mixed into this. So I don't need the multiply either. And I also don't need this throttle anymore, because now in the circuit there's a hardware clock. Okay, well there's two. There's the microphone and the hack RF. So I don't need the throttle anymore either. So I can clean this right up. So this bit here was just to get my voice centered around the half, so I could swing between 0 and 1. So the output of that doesn't even need to be there either. The output of that can go straight to here. So that will modulate this between 0 and 1. So if you put a 1 into this Osmocom, it would send it out at its full power. If you put a 0 in, it'll be nothing. So that's that. I don't need this times. Should I have that? I'll just press D for disabling that at the moment. We might come back to that. Anyway, I'll run that and see what happens. So all my displays have gone. And here's the real world RF. Now again, there's going to be a bit of a delay. So it only just came up now. So that's that. So anyway, I have to find some optimal values here. But for now, it's coming in pretty strong. So if I speak, and I'll turn this volume up, it's a huge delay. Oh, and unmute it. It's coming in pretty strong. So if I speak, and I'll turn this volume up, it's a huge delay. Oh, and unmute it. So there you go. That's oh shit! I've even got feedback coming in. It's a massive delay. That's to do with the RTL SDR server on the thing. Okay, I'll just mute that. You get the idea. RTL SDR server. There you go. Okay, I'll just mute that. You saw what happened though. I'll just keep speaking while it's doing it. We have the carrier in the middle there, which is what you expect, and that's what you tune into when you lock into stuff. But you can see it modulating from side to side. And if, as I said before, the higher the frequency, because they're mixing, the higher the frequency that's mixed with it, the further out from that center frequency it'll be. Like if I try and whistle from low to high and high to low, like what you should see in a second when it comes through is that should go from low to head out like that, and the high one heading back in. Okay, so what you can work out by that is the bandwidth that this whole thing's going to take will be 2 of the maximum frequency that's being modulated. So let's say I put a filter in here and make it so you only use like 5 or 6 kilohertz. That'll be like 10 or 12 kilohertz bandwidth for the whole thing. So that's an AM transmitter right there. Okay, I've just tuned into a commercial AM station here, and you can see we've got the carrier all the time. That's the big thick red one here. And as they talk, if I unmute them, a bit of music.
News. Good morning, I'm George Roberts.
Okay.
One man is on the run.
Oh, man on the run. So you can see quite clearly on theirs, the sidebands that only come up when they speak. When they don't speak, because he's just announcing news at the moment, you just have the carrier. And that's about it. So the way to see that a little bit clearer than I had before, you can boost up the FFT size, which will narrow the resolution bandwidth. Okay, that gives you a bit of a finer grain look on it, but of course it won't be as responsive. Let's see, you can sort of get an idea there from a commercial station. So that's how AM looks, and of course I can just run that.
Travelling on the Bruce Highway just before 5 p.m.
So that's an AM radio station. We just made one essentially. Not that I can transmit on this frequency, but you get the idea. Now I'll go back to my fantastic one. Let's just send something out here, put some gain in, so we can actually receive it, and something should pop up. There it is. So there's me. Okay, so there's my my AM transmitter. You can hear me in the background. And I've got to tell you, it's pretty clear. So that's all good and well, but let's have a look at this now. Just hang on, let me just mute that to hear myself. If I have a look at this, what's going on here, center it right up. Okay, that's as good as any AM transmitter, except you see how it's still going all the way out to here? That's because I've got no filtering going on, so that'll go as wide as I showed, the bandwidth that I'm speaking. So in the real world, you'd put a filter on before you transmit it, so you keep the bandwidth to whatever you're trying to keep it to. So if I do that whistle again, it should be clear. There, see, nice and clear. Okay, so that's that. Now what about the power? Now if I'm not speaking, there's only a carrier. And if I speak, then there's extra RF energy on the sides here. But when you think about it, there's a lot of waste in AM, and this is the thing about it. The carrier doesn't transmit any information as such. It's just a carrier. It gives you something to lock onto, but that's about it. And the sidebands, well, one's in phase and one's out of phase. So there's no extra information as such, though. This part here is all you really need for all the information I'm sending, which is the baseband, my voice. See, that's me just being quiet for a bit, and what you saw was just the carrier. So the carrier is always putting energy out, and then when I start speaking, you get these sidebands over here. Now, one doesn't contain any more information than the other. It's not like there's low frequencies here and high frequencies there. It's all here. That one's just the inverse on the lower sideband. So there's power wasted essentially that doesn't give any new information over the air. That's the carrier and one of the sidebands. And that's why you might have heard of single sideband transmissions. They get rid of this so they can run on lower power, but you need a more complicated transmitter and receiver. As you saw, this was pretty easy to set up, so that's why this is used. If I just go back to one of the early ones here, I want to talk about modulation index just briefly. So you can see that if I'm not talking, I've just paused it, the red one, which is my voice, doesn't move. So the whole energy that this thing's putting out, if that was a transmitter, would be purely for the carrier. And then as I talk, it modulates that, as I've pointed out before. But see where I'm talking, if I just get rid of the green one for a minute. Alright, what you can see here is my voice centered on 0.5, so it can swing up to 1 and down to 0. So maximum and minimum power for the transmitter. But as I speak, you can tell that the maximum only goes to, let's say, 0.7-ish. Like it never reaches up to 1 or goes down to 0, unless I really shout, and that's not my normal speaking voice. So my normal speaking voice is about here. So what I'm going to do is I'm going to put a bit of gain on this, just so I can adjust that. Okay, so where my sound comes in, I'm just going to add a basically an input gain control. Okay, so before it gets to anything, I'm going to put a multiply constant. I'm going to stick that in between there. Right, so I'm going to multiply the input from the sound card by something. So I'll multiply it by something that I'll have in a range. And I'll make that range, I'll call it mic gain. Default value is 1, it starts at 0, goes up to 10 in 0.1 increments. And I'll call this constant, instead of saying multiply it by 1, I'll multiply it by whatever that mic gain variable is. So when I run that now, get rid of the carrier. You've seen the carrier before, it's never going to change. You see that here. So now I've got a mic gain. If I just get rid of the modulated output, you'll see as I turn the gain right to 0, it doesn't matter what I say, it's stuck here on 0.5. And if I go right up and over, and go way over, you see it's going nuts, way past everything. Okay, so if I put that modulated output on again, what I can show you now is, well, it was gain 1, so that's what it was before. And I'm just talking, you can see it varies between there and there. If I turn it up a bit, because I've still got room to move here, given my normal voice, I still haven't gone past 1, I'm trying to keep within this, between 1 and 0. Now we know though that if I go past that, if I go over, I still haven't quite made it there. So if I speak a bit louder, what's happened there is I've gone below 0, and you remember before, what happens is the modulated signal will be out of phase. I've over modulated that. So ideally, you'd have that just between 1 and 0, which would be 100% modulation. Anything less is less than 100%, anything more is over modulated. So if I'm not modulating at all, then all of the power that goes out of a transmitter is purely for the carrier. Okay, like if I let's pause that. If I'm not doing anything, all the RF, which is what the green one essentially is, that's what's going out in the air, all of it is simply the carrier. There's no information at all. But if I get perfectly matched 100% modulation, which I'm never going to do here, you get the idea, I hope, in a very badly explained video that I didn't plan at all. Oh, it's really fucked. Anyway, if you manage to get 100% modulation, then that's about as efficient as it can be. But even then, one of those sidebands that I showed you before, in a perfect world, would still only be a sixth of the power. You've still got the other sideband doing the same thing, and you've got the carrier sticking way up the middle with most of the energy, which doesn't convey any information. So that's what I mean by it's not the most efficient transmission method, but it is certainly the simplest. So anyway, I just wanted to show you that. Now this diagram's a bit messy and hard to follow, and just like my cables in the real world, I like my diagrams to be nice too. So what I'm going to do is I'm going to neaten this right up and tweak it a bit, add that volume to the input here, maybe add a mixer to some other sort of music, a different input, and I might put a little frequency sync on the end here and tidy it up and just to give you a dummy view of what might come out here, which means I'll have to produce whatever this carrier is here just so I can visualize it here without having to use a real one. Okay, so I'll just tidy this up. Okay, now I like my cables tidy, and I also like my diagrams tidy. So after a bit of cleanup, I ended up with this. So I got the microphone input there being multiplied by whatever the gain range setting is, and I'm just showing that on the time sync there, the scope, so you can see the audio coming in. And this section here is where I offset it up to be centered around 0.5 instead of 0. And this here is just to show what it would look like going out in the air. This isn't actually required for anything up here. This is just imitating the local oscillator in the Hack RF, just so I can mix it and have a look at what the spectrum does look like out in the air. So anyway, the audio that comes out here goes into a virtual sync. Now this is simply a way to connect to a virtual source, so that it saves you doing something like this and having a big line across your diagram. You can just put it into a virtual sync and then continue on from that virtual source as long as they're named the same. So that goes into there. Now down the bottom we've got the RF section. So I've got these floating units going to make a complex output. That gets resampled up to the higher rate for the transmitter, with a final little button here, sorry, a little box for transmission, which I should name transmit nicely. Okay, so that means if I don't have that enabled, it won't actually transmit. And what I've also done is added a tab widget here, and all these audio things here I've put in the GUI hint. I've set them to be the first tab, and then the RF ones to be the second. So I'll just show you. That looks if I just drag it over here. So now I've got a couple of tabs up here, one for the audio and the audio stuff, and then one for the RF. And now I've got a button to actually transmit. So now it transmits, and that's that dummy display. If I show the real one, it's over here. So if I stop transmitting, it stops transmitting. It just gives me a way to see what the spectrum looks like. So that matches what this is up here, essentially. So that's that, and I can modify all the other stuff. Oh, and one other thing I did with the gains, this RF gain and IF gain, that does set the transmitter, but since I've got this multiply by 0 or by 1 to actually transmit, in here I just multiply that by transmit 2. So if I'm not transmitting, the gain and IF gain gets set to 0. So it completely shuts off the output. Okay, so that way, there we are there. Get the other one. If I'm not transmitting at all, that's flat out dead, which is what I want. So there it is. I'll just turn this up. You'll hear it still works. You'll hear a bit of a delay, echo. That's me, and it works fine. That's AM going through the air. Again, I might put filtering on so it doesn't just spread out the bandwidth really high, but you know, this is just to This is just to show you the concept. Okay, so there you go. In the coming videos I'll do more of this, but there may be a bit more trigonometry coming up too, so you might want to brush up on that. But I still want to keep it just reasonable. I don't want to get carried away into ridiculous engineering formulas that you're probably never going to use. So that'll do for now. Until next time, take it easy.